So now we're going to move on to number 4. So the molar mass of an enzyme determined by dissolving in water, osmotic pressure. So they're doing this by concentration versus the height of the liquid it's supporting. We talked about this in class. It's in your book. So obviously concentration, milligrams per centimeters cubed versus height. So what I'm going to do is just show you real quick here a few things to look at. One of the equations is, we started off, which was mole fraction. This is just a derivation, so to speak. So the mole fraction of the solute looks like this. And you can see how this can be broken down to moles, and you can make an approximation. When this is really dilute, solute is dilute, you can approximate that. You have moles, solute over moles of solvent, right? So you could take that, put it over here for the mole fraction. We know that molar volume would be the volume per moles of solvent. So you can see how moles of solvent will cancel, leaving you with this. So moles of solute per volume, that's just the concentration. Moles could be replaced by little m over big M. See the V still there? So you see how you have M over V. That's concentration in terms of things like grams per mil, right? And you leave that M down there. So this is one popular way of writing osmotic pressure in terms of the concentration of something in grams, or milligrams per liter or milliliter. Next up is another way of looking at osmotic pressure. So there's a whole bunch of formulas here. Osmotic pressure is equal to the pressure, which is force divided by area, which is also m times g over area. But we know that the density of the liquid being supported, it looks like this, solve for m, PV. So what are we doing? We're replacing a few things here. We can replace m with rho v, right? So all we did was take for m, we put in rho times density times volume, right? But volume divided by area is nothing more than the height, because height times area gives you volume. So that volume divided by area gets replaced by height. So this is the classic derivation of this formula, which is useful. So we have osmotic pressure equaling this, but it also equals this. So set these two equal. So now you've got, let's isolate molar mass. So one way to calculate molar mass, if you had it, was this way. But what if I wanted to graph something because I had a whole bunch of data? Well, we have H and we have C. So I'll rearrange it, and maybe I'll put H on my y-axis, and I'll put concentration over here. Y equals mx. So you plot H versus C, and one of the things I got for my answer is the slope is that much. So now you take that slope and set it equal to this, and then solve for m. So you can see how you have the slope equaling that, and then you solve for m. There's a whole sort of rat's nest of units for you to take care of. I can tell you that your answer could be something like somewhere between 11 and 15,000 grams per mole, or could be 11 to 15 kilograms per mole. If you choose grams or kilograms, that's kind of your answer, somewhere in that range when you do this one right. So that's number